Hello, Math 119 students. So this video is a continuation of the first video for the central limit theorem, which is in chapter 7. So here's what we'll go over what happened during the first video as a summary. So with the first video, we simulated a population which had a mean of 69.5 and a normal distribution, such as this one here on the left side of this diagram. And then what we noticed is that when we took small samples, our sampling distribution for a size of 2 it was centered at the 69.5, just like the population, and it had a normal distribution, just like the population did, but it was a somewhat narrower distribution than the population. And then when we increased the sample size to 30, the sampling distribution also had first of all, it was centered at 69.5, just like the population, and it had a narrower distribution, but it was still a normal distribution. So now what we're going to do is we're going to look at two other distributions. If we have a population that doesn't have a normal distribution, such as this uniform distribution or this skewed distribution. So theoretically, here's what happens. When we have a small sample size, the sampling distribution for a small sample size of 2 should have not a bell-shaped distribution, but a sort of a triangular distribution. But then when we increase the sample size to 30, our sampling distribution should become bell-shaped. And then when we have the skewed distribution, our population distribution is skewed like the third one, then when we have a small sample size, our sampling distribution should be more bell-shaped than the population, but somewhat skewed to the right, as we have here in the middle. But then once we get to a sample size of 30, the population of the sampling distribution of the sample means should become normal again. So in other words, regardless of whether we have a normal, a uniform, or a skewed distribution, once you get to a sample size of 30 or more, the sampling distribution should all look the same. They should have a bell-shaped distribution centered at the mean, and they should all look pretty much the same. So let's see what happens. Okay, so here's our uniform distribution. So to start with, we'll take a sample of size 2. So theoretically, what it should look like, our sampling distribution should be, as it showed on the diagram, sort of triangular. But the mean should still equal, the mean of our sampling distribution should still equal the population mean. And this time the population mean is 25, and the standard deviation of the population distribution is 14.43. So let's take one sample, and we'll start to build up the sampling distribution for samples of size 2. So here's our first sample mean. It's about 36. Let's do it again. That time we got 27.4. Okay, let's do it 5,000 times, just like we did when we had a normal distribution for the population. Okay, now we've reached 5,000. So theoretically, the sampling distribution should be kind of triangular shape. Well, that's what it looks like to me. It looks sort of a triangular shape, just like it showed here. So it should have a triangular shape. Well, it seems like it does to me. And then, but also it's another thing that's important is we have 5,000 sample means. What's the mean of the 5,000 sample means? Well, it shows right here, 24.989. Well, that's very close to the population mean, which is 25. And then the standard deviation of our 5,002 sample means is 10.296. So theoretically, the standard deviation of the sampling distribution should equal the population standard deviation divided by the square root of the sample size. Well, that would be 14.43 divided by the square root of 2, and that's 10.2. So theoretically, the standard deviation should be pretty close to 10.2. So we got 10.296, so it was pretty close. Okay, now let's reset it and increase the sample size to 30. So now theoretically, the shape of our sampling distribution should be approximately normal. Okay, so if we take one sample, here's one sample. Our sample mean was 20.78. Okay, so now let's do this, keep going and do this 5,000 times. Now we have 5,001 sample means. And then first thing, it's important to notice that the mean, once again, the mean of our 5,000 sample means is 25.0162, very close to 25. And then the standard deviation is 2.6392. Well, theoretically, the standard deviation should be 14.4309 divided by the square root of 30. And that equals 2.63. So the theoretical standard deviation is pretty close to what we got, which is 2.6392. And also now, as far as the shape is concerned, notice that the shape is no longer triangular. It looks pretty close to a normal distribution. Okay, I want to do one more. And now we want to look at the, if we have a distribution that's skewed to the, highly skewed to the right, like this one. Okay, so we can do that here. So we will do this over again. So now we're going to look at a right skewed distribution. Let me pull this over. So here's a really right skewed distribution that we have. So now once again, we'll take samples of size 2 and samples of size 30 and see what the sampling distribution looks like. So now I'm just going to jump right ahead and take 5,000 sample means, now that you get the idea of what's happening. There's 1,000, 2,000, 3,000, 4,000, 5,000. So we have 5,000 sample means where the sample size is 2. So first of all, let's look at the mean of our 5,000 sample means. It's 14.0509. Well, the theoretical mean of our population is 14.0519. So those are very close. Then the standard deviation of our sampling distribution, of our population distribution is 11.8255. The standard deviation of the 5,000 means is 8.4415. Well, the theoretical standard deviation should be 11.8255 divided by the square root of 2, and that equals 8.36. So 8.4415 is pretty close to 8.36, which is the theoretical standard deviation. Then notice the shape. The shape of the distribution is not bell-shaped. It's also, it looks skewed. It looks pretty skewed to the right. Just the way it should look, according to this chart here. It should have a skewed shape for a sample of size 2. Okay, the last thing I want to do is I want to increase the sample size to 30. Okay, so we'll reset it. Okay, now let's do take our 5,000 sample means. Okay, so we'll look at the 3 major things. Let's look at the mean of our 5,000 sample means. 14.0589, very close to the population mean. Then the standard deviation of our 5,000 means, 2.1498. So the theoretical standard deviation should be 11.8255 divided by the square root of 30. But that equals 2.159. So 2.1498 is pretty close to 2.159. And then the most important thing, what's the shape of the distribution of our 5,000 sample means? That's the green distribution on the bottom. Here's the distribution of our 5,000 sample means, and you can see that it looks pretty close to a normal distribution. Pretty bell-shaped, quite symmetric, and pretty close to a normal distribution. Okay, so now we have verified the central limit theorem for three cases: the normal distribution, the uniform distribution, and the skewed distribution. But the central limit theorem is valid even when you have some general distribution like this green one on the upper right. See, when you have a kind of a general distribution, for small samples, you won't have a normally distributed sampling distribution, but if you take a sample of size 30, it becomes bell-shaped. So notice, regardless of what the population shape is, the shape of the sampling distribution will be centered at mu and have a normal shape. And that's what number 3 says. Number 3 says the shape of a sampling distribution of sample means will approach that of a normal distribution, regardless of the shape of the population distribution. That's what we just showed. The larger the sample size, the better the normal distribution approximation will be. So if we increase the sample size high above 30, we should get an even better normal distribution. Okay, so that's basically what I want to show. Actually, let's look at example 1.1 before the video finishes. So example 1 says calculate the standard deviation for a sampling distribution of sample means using the central limit theorem. So here's what we have in this example. The standard deviation, that's sigma. The population standard deviation is 0.72. And it says if you take samples of size 52, so that's our sample size, 52, what would be the theoretical standard deviation of the sampling distribution? Okay, well, that would be sigma, which is 0.72, divided by the square root of the sample size. So that would be 0.72 divided by the square root of 52. And we call that sigma of x bar. So sigma of x bar will equal, let me calculate it with my calculator. Well, it's about 0.1. So 0.72 divided by the square root of 52 is about equal to 0.1. So that's it for this video.